What I want you guys to just take note of in terms of probability is the fact that on your formula sheet, we only give you the probability rule. So the thing in the green blocks up at the top there, as well as the basic formula for probability that you sort of learned from grade 8. All right, so the thing in the double green blocks that you get given on your formula sheet, which is very useful because you'll see as we go along, depending on the type of event you have, this formula changes a little bit. But you are given, I'm trying to get everything in here on the screen. Let's see how we go. So you are given this formula, and you are also given, although to be perfectly honest with you, I don't think anyone would need this. You are also told that probability, okay, we'll do it here and then I'll move it up. The probability of any event that we're talking about is found by taking the number of outcomes in that event, or that satisfy that event, divided by the number of outcomes in your sample space. Those are the only two probability formulas that you're given. Now, that's really important to note because when we get to independent events, so you can see down here on the far right-hand side, you are not given the formula for independent events. You have to know that. The two with a pink tick you get, but that's it for probability. You do not get the rule for independent events, and you do need to know that because often we ask you, are these two events independent, or prove that they're independent, or we tell you that they're independent and you need to use that fact. So probability rule you're given, independent you're not, and you need to know it. Alrighty, so before we get into all of this, can someone tell me what probability is? So like when we work with probability, what is that actually? And you can unmute yourself if you want, or you can just type it on the chat. What is probability? Nice. Okay, good, Awami. It's how likely or unlikely something is to happen. So some event, really any event, how likely is it to happen? So we could say it is the likelihood of an event occurring. Now, what I want you guys to remember is that probability is a scale, essentially, or can be placed on a scale. So what I mean by that is we get the probability or the likelihood of 0 all the way up to the likelihood of 1. What you need to remember is that you should never get a probability value that is less than 0, so negative, or greater than 1. Because if it's greater than 1, it means that there's more than 100% chance of something happening, excuse me, which is not possible. It either is certain or it's not. And if you get less than 0, then you're saying there is a less than impossible chance of something happening, which also is just not possible. So your probability exists on a scale between 0 and 1. My advice is, if you're typing it into a calculator, just leave it as a fraction. But probability exists in that scale. You can express probability, as I've already said, as a fraction. Generally speaking, I would just leave it like this because if you're doing calculator work, your calculator automatically gives you a fraction. You can leave your answer as a decimal, or you could give your answer as a percentage. Now, it makes absolutely no difference which one you leave your answer as or which one you give your answer as. Only time we will mark you according to format of your answer is if the question had, for example, said, calculate the probability as a decimal of this event occurring. Because then in the question we said as a decimal, we expect you to write it as a decimal, and then we're going to mark you accordingly. But if it doesn't say, makes no difference which one you want to go for. Usually we work with fraction and decimal, but again, really makes no difference. Sorry, frog in my throat. Okay, so We have got a bunch of different types of events that we need to be comfortable working with, and each of these events have a characteristic that defines them and that is going to help us answer questions when we're talking about mutually exclusive events or independent events or complementary events or whatever. Okay. Oh, excuse me. Clearly it's the end of term. For each of the three events that I want to chat about, or each of the first three events I want to chat about, I have a little diagram there. Can anyone tell me what that diagram is called with the circles? So what are these diagrams called? What type of diagram are they? Nice, Alami. Okay, these are called Venn diagrams. We're going to talk about Venn diagrams a little bit more on Wednesday, but they're called Venn diagrams. Nice, Leila. It is a way that we represent probabilities or events visually. Sometimes it's very useful for us to use a Venn diagram to see what relationship our events have with each other. Okay, so the first type of event that we have is a mutually exclusive event. Now, mutually exclusive events are events that have no outcomes in common. Now, we can see that in our Venn diagram because there is no intersection between our events. No common outcomes. So if you were to look at a Venn diagram and you saw that the two circles did not intersect or did not overlap with each other, you then know that they are mutually exclusive. What this means in terms of our probability rule is that the last term in our probability rule, that minus probability A and B, you're actually subtracting 0. So the probability of A and B, so the likelihood of both of those events occurring at the same time, so the overlap, is equal to 0. That is what a mutually exclusive event is. So if I tell you events are mutually exclusive, you automatically know that the intersection or the probability of A and B is 0. When we get to exhaustive events, now I'm not saying we don't ever use these, it's just not used a whole lot. Generally, we use mutually exclusive and independent events in assessments, but you need to be aware of both complementary and exhaustive because we can test you on them. So exhaustive events are eventually events that together, all of their outcomes form the sample space. So you can see in this Venn diagram, all of the outcomes are either in A, B, or in the intersection between. There is nothing that exists in the square outside those two events. So the probability of A or B happening is 100%. You're either going to get an outcome in A and B, or B. So exhaustive events are events that fill the whole sample space. And so again, what this means in terms of our probability rule is that the probability of A or B, I don't care if it's A, I don't care if it's B, I don't care if it's A and B at the same time, but A or B is 1. It's going to be one of those two. Because everything is contained in my events that I'm working with. Complementary events are special types of events that are both exhaustive and mutually exclusive. So not only do all outcomes fall in one of the events are also mutually exclusive. They have no intersection between. So again, if you look at the Venn diagram, there's no intersection, as well as the fact that all outcomes exist in one of those two circles. Okay, exhaustive events, it's not really like a rule for it. I don't know why I said exhaustive events. I mean complementary events. Complementary events not there's no rule for it, but what we need to bear in mind with the complementary events is that if you want the probability of one of your events occurring, so if we wanted the probability of A, we would say 1 minus the probability of not A. We could also say it the other way around, the probability of not A is equal to 1 minus the probability of A. Now, what this means is, if we wanted the probability of A in this Venn diagram, so the probability of that one circle, essentially because of the fact that, sorry, so going straight here, because of the fact that this event is exhaustive, so if it's not going to be in A, it has to be in B. And because of the fact that all of the events will either be in A or B, we know that if we just subtract the outcomes we know are not in A, we are left with what is in A. So we're left with the probability of A. So complementary events, if you want the probability of an event, you basically just subtract the probability of everything outside that event. So not. That's how we phrase everything excluding that event. We say not. Not, we can also use a little apostrophe for. I think I've got an example later on, but if not, I will draw it in for you. But that's essentially what complementary events are. They're both exhaustive and mutually exclusive. Because of the fact that they are both of those things, if you wanted the probability of event A, you would just say 1 minus not A. So everything outside of A. If you wanted the probability of event B, 1 minus not B, everything outside of event B. Right, independent events is not really something we can visualize. But independent events is where the probability of one event is not influenced by whether or not the other event occurs. So for example, your shoe size does not affect your maths mark, okay? Those two would be independent events. Whatever your shoe size is has no effect on what maths mark you get. So they are independent of each other. Boy. Right, now the probability rule, which I will write down in a second, is one that you do not get, but one that you need to know. I can guarantee you that they are going to ask you something to do with independent events. So you need to know the rule. Stupid thing. Right, so this rule, I'm going to write it in a different color because it's one that you need to know. Like I said, I can guarantee you, you're going to be asked an independent events question. Is the fact that the probability of A and B is equal to the product of the probabilities of A and B. So probability of A and B is equal to the probability of A times the probability of B. Let's think of this much. And again, guys, this is one that you need to know. You are not given this rule. It's not on your formula sheet. You need to know the independent rule formula. Like I said, I can guarantee you they are going to ask you a question on independent events. Pretty much guarantee it. And so you need to know that rule. That's the only one that I would advise you learn. I feel like the rest of these little rules I've put in green are self-explanatory. If you struggle, though, with understanding what each of these events are, then it is useful to know those little rules or little characteristics of the events. But independent events, you have to know that rule, and you are going to be asked it, so know it. Right, I'm just going to wait here for a second for you guys to take a screenshot of the summary, and then we're going to have a look at some examples of how we now use these characteristics of these events in questions. Remember, if you got questions, just ask. Right, the thing with probability is you need to read your questions carefully. Make sure that you understand all the information that's been given to you, and you make sure you understand which rule it is you need to apply when. Okay, so let's look at our first example. Let's just make this a bit bigger now. All right, so example 1. We've got a 6-sided dice, whatever you prefer, it really doesn't matter. Die is technically grammatically correct for the singular. I don't care. Okay, dice, we're happy, but if you see die, it means a dice. A 6-sided die is rolled and the number on the landing face is noted. So landing face is how it lands. If it lands with a 4 up, that would be the landing face. Consider the following events. So we've got event A, number less than 3. Event B, even numbers. And event C, the number 4. So before we get into any of these questions, what I first want to do is I want to actually make sure we know what events are in each of these. So a number less than 3 on a die or dice would only be the numbers 1 and 2. Those are the only 2 numbers less than 3. Even numbers would be 2, 4, and 6. And obviously the number 4 is just quite literally the number 4. So the first question says, what is the sample space? Can someone tell me what a sample space is, or what is the sample space? So you don't actually have to give me the answers, but what is a sample space? When I refer to sample space, what do I mean? Nice, Owami, exactly. So Owami said it's all the possible outcomes, 100%. That is exactly what a sample space is. In a Venn diagram, if I just scroll back up here, the block represents your sample space. So everything contained inside your block should contain every single possible outcome for the event or the experiment that you're looking at. So when you are asked for the sample space of whatever event or whatever experiment, what I'm asking you for is all the possible outcomes. It's actually all possible. Now, grade 12s, when you are asked to list a sample space, I don't know what I did there. When you're asked to list a sample space or give a sample space or give all the outcomes that exist or that fall into an event, we use a curly bracket to contain the list that we're about to write. So S is sample space. So we're saying S is categorized by the numbers 1, 2, 3, 4, 5, and 6. Those are all the numbers on a die. So that is my entire sample space. Those are the only possible outcomes I can get when I roll an even or fair die. I'm then being asked in question B for some probabilities. Now, this is where this formula over here comes into play. Now, guys, again, I don't particularly think you ever consciously think, oh, I'm using this formula. Obviously, if you do, that's absolutely fine. But we know that to determine the probability of an event, we take the number of outcomes that fall into the event and divide it by the total number of outcomes. So if I wanted the probability of event A occurring, event A are numbers less than 3. How many numbers less than 3 do I have on a die? Okay, I've only got 2 numbers. So that's 2 out of my total possible 6 outcomes. 2 out of 6. So my probability here of event A is 1/3. Now, technically, grade 12s, you don't have to simplify. It's not actually something we're super strict on. I always simplify. I just think mathematically, you should always simplify your answers. But if you forget to simplify, it's not the end of the world. Okay, your teachers might be different. Some teachers are quite strict with simplification. I used to be very, very strict with simplification, but I've learned to let it go a little bit. But my advice is always simplify. It's just mathematically, we should always be simplifying our answers. Right, probability of B. How many outcomes do I have in event B? Even numbers. So how many even numbers do we have? Nice, Awami, nice, Leila. Okay, we have got 3 outcomes. So 3 out of a total 6. So the probability of event B occurring is a half. Right, probability of event C, I've only got 1 outcome there, so it's just 1 out of 6. Now again, great tools, I said to you that there's 3 ways you can represent your answer: a decimal, a fraction, a percentage. If you wanted to write this as 33.33%, 50%, and 16.67%, fine. If you wanted to write all of those as decimals, fine. But personally, in our head, the probability rule is already a fraction. So we're already going to write it as a fraction anyways. Leave it as a fraction. Unless the question specifically said, determine the probability of A as a decimal, as a percentage, leave it as a fraction. There's no need to do extra work. All right, the next question says, it doesn't say any of that. It says, determine the probability of P dash. Right, this little dash here means not. So what this is actually asking us is the probability of not A. Now, there's a couple of different ways that you can go and do this, but remember, if we scroll back up to our little rule here, we spoke about the fact that complementary events are events that are both exhaustive and mutually exclusive. Okay. Where I'm going with this. Righty-roo. If we wanted to work out the probability of not A, essentially I want you to work out the probability of everything else occurring except for A. So that's what not A means. I don't care if it's B or C. I do not care if it's none of those. I just do not want it to be A. So to do that, there's no need to try and overcomplicate things. What we do is we say, okay, cool. The probability of not A. If you want to use the A dash, that's obviously absolutely fine. There's nothing wrong with that. Just get rid of that. The probability of not A. Now, you could go and say, okay, cool, I'm going to count how many outcomes I have in the others. So I've got 2, 4, 6, and then 4 again. So I've got 4 outcomes that are not in A. But remember, 2 is an A. So we need to be careful of that fact. If you wanted to draw like a little Venn diagram for yourself, that's absolutely fine as well. So if you wanted to visualize what's going on here, you could. Ooh. A, B, C. So between A and B, we've got an intersection with 2. Between B and C, we've got an intersection of 4. A then has 1 in it. This has 2 and 6 in it. But those are definitely exhaustive events. All of my outcomes, no, it's not an exhaustive event because I'm just talking nonsense. And there's my sample space. So the numbers 3 and 5 are not in any of those events. Okay, so not A means everything else except for A. So there's a couple different ways you can do this. I find a Venn diagram a lot easier to work with. Ooh. You could just ignore everything that's in A and you can work out your probability from there. You can, oh, my pens are gone. You can also use the formula, and Layla suggested that as well, which says the probability of not A is 1 minus the probability of A. Now, I would find that a lot easier to do, I agree, Layla, because of the fact that we haven't been asked to draw a Venn diagram. So at no point were we asked to do this diagram, which means that technically we don't have this visual aid for ourselves. So absolutely, you can go and do the extra work and draw the Venn diagram, but we don't have it. And in a test or an exam, why create more work for ourselves? When we've got a little formula or a little rule that we can use, to go and work it out. Now we have already in question B worked out what the probability of A is. So we would say 1 minus a third, and obviously I don't have enough space, which equals 2/3. So the probability of getting anything except A is 2/3. Now, if you go back and use your Venn diagram, which obviously I've now crossed out because those are choices that I make in life. So let's just get rid of that. If you were going to ignore everything in A and then consider everything else, so we're going to ignore everything in the circle, including the 2, even though that does fall in B, what you can see is that we have got 1, 2, 3, 4 outcomes. 4 out of a total 6 outcomes. 4 over 6 simplified is 2 over 3. So it doesn't matter how you choose to do this. If you want to use a formula, go for it. Personally, I would probably use the formula because it's nice and quick and easy. You don't then have to draw a Venn diagram. If you are someone who's visual and you need to see how the events link, draw a Venn diagram. Nothing wrong with that. You're going to get exactly the same answer anyways. So how you choose to do it, completely up to you. I personally would use the formula as well, Leila. But if you need the Venn diagram to help you, draw one. Okay, that's why we have these tools of visualization in maths. Right, so question B says, are the events mutually exclusive? Now we need to be careful here because we've got 3 events. So we need to compare A and B. We need to compare A and C. And we need to compare B and C. And we want to say whether or not those events are mutually exclusive. Now, this is where a Venn diagram is helpful, because for me in my head, to go and substitute all of that into my probability rule and then to work out whether or not there's an intersection, that seems like a mission to me. Whereas with a Venn diagram, I can clearly see if there's an intersection that exists or not. So between A and B, I definitely have an intersection. Remember, 2 was in both of them. So these are not mutually exclusive. So many words to have to write. Because 2 is an outcome in both. And it does, oh, it didn't say give a reason, but we're going to give a reason. Right, A and C. Look at A and C. Is there anything that falls into both A and C? So is there an intersection there? Good. Right, so when we said no, exactly, there is no intersection. We can see that between A and C, there is nothing that falls in both A and C. Because there is no intersection, it means that they are mutually exclusive. Because remember, mutually exclusive events, no intersection, no overlap. And the reason no common outcome, or you could say there's no intersection, that's absolutely fine as well. Or if you wanted to be fancy and write it in mathematical terms, you could say that the probability of A, let's maybe try that again. The probability of A and C is equal to 0. There is no intersection between A and C. Finally, between B and C, are they mutually exclusive? Have a look. See if there's an intersection. Are they mutually exclusive? Good. Again, no, they are not mutually exclusive because they have got 4 in common to both of them. Right, now we can and we will eventually get to a point where we're proving this with the rule. For now, it's just important that you can see when there is an intersection, they're not mutually exclusive. When there isn't, when there is, they are. Okay, but generally speaking, if we ask you that are they mutually exclusive, we'll say something along the lines of justify your answer with relevant calculations. You then use the probability rule, and we will do that a little later. But just understand, if there is an intersection, not mutually exclusive. If there is no intersection, mutually exclusive. Right, the last question says, determine the probability of A or C. Now, again, you've got a couple different ways that you can do this, and it is completely up to you how you choose to do this. You can use your probability rule. I don't know why I said the last question. There's still 2 more questions. Clearly, I'm losing my mind. You can use your probability rule, which I'll show you how to do now, or you can use the Venn diagram. Again, whatever you want to do. It is completely up to you, whatever makes more sense for you. Okay, so I'm going to use a Venn diagram to start off with, just because then we can use that to check whether or not we got the right answer with our probability rule. So what's the probability of A or C? What that means is I don't care if it's an A only, I don't care if it's in C only, I don't care if it's an A and C, I could not care less. I just want to know that it's in one of them. So we've got 1, 2, and 4 as outcomes in A and C. Yes, 2 and 4 are in B, but we don't care about B. B hasn't been mentioned. So there are 3 outcomes of the possible 6 that fall in A or C. So the probability of A or C, it's quite an excessively thick pen, but anywho, is the 3 out of a total 6 outcomes. So you've got a 50% chance that your outcome is in A or C. Right, if you wanted to use the probability rule, now remember this is on your formula sheet. The probability rule says that the probability of A or B, so in this case A or C, is equal to the probability of A plus the probability of C minus the intersection between the 2 of them, so A and. Great, we already know that A and C are mutually exclusive. So we already know that their intersection is 0. And we've worked out the probabilities of A and C in question B. So we have all the information that we need. The probability of A, which was a number less than 3, was 1 out of 3. Plus the probability of C, which was the number 4, which is just 1 out of 6, minus 0. Chuck it into your calculator. That's all you need to do. So if you didn't want to chuck it into calculator and for whatever reason you wanted to find an LCD, it would be 2 over 6 plus 1 over 6, which is 3 over 6, which, if you have a look, is exactly the same thing that we got, a half. So again, I don't care if you use a Venn diagram, I don't care if you use the rule. In situations where you can use either, you pick what you are more comfortable with. All right, there is no rule that says you have to use the probability rule. There's no rule that says you have to use a Venn diagram. Use what makes most sense for you and what you are more comfortable with. All right, so with all of that being said, I want you guys to try question F, which is determine, okay, there should be a P there, I'll put that in now, the probability of A or B. So we've just done an or question, the probability of A or B. You can use the Venn, you can use your rule, whatever you want. I'm going to give you a minute, try it, and then we'll have a look. Okay, while you're trying, there's a question of how many marks is a Venn diagram worth in a matric paper? If it's asking you to draw the Venn diagram from scratch, it depends on the number of circles, so the number of events. At a matric level, you're generally working with 3 events, so 3 circles like we are here. So you would likely get a mark for the middlemost intersection between the 3, a mark for the events in the 3 circles, and then maybe a mark if there is values outside of your events just in your sample space. So anywhere between 3 to 5 marks for a Venn diagram. You'll see on Wednesday, I think it was a past paper question that I put in, if I remember correctly. What they sometimes do with Venn diagrams is they give you a partial Venn diagram and there's an unknown. So there'll be like an X or an A or whatever, and you're going to have to solve for it. But if you're drawing one from scratch, anywhere between 3 to 5 marks. And that's 3 to 5 of the 15 marks, or whatever we said probability was. Obviously now I've forgotten. Sorry, I'm going to come back. Now I'm just feeling silly. Of the 15 marks. So it is a fair chunk if we ask you. I'm sure you will remember that Venn diagrams aren't very nice to draw when you have so much information that you need to put onto a Venn diagram. Obviously, it's important that you do, but it's more likely that they'll ask you to calculate missing information from a Venn diagram. I'm not saying that they won't ask you to draw one, they definitely can. Tree diagrams are more often asked of you to draw over Venn diagrams, just because tree diagrams are a little easier to draw. Right, probability of A or B. So again, you can use a probability rule or you can use a Venn diagram. If we go to the Venn diagram, A or B, so I don't care if it's A, I don't care if it's B, I don't care if it's A and B. So A, we've got whatever that was trying to be. So A, we've got 1, 2, 6, and 4. So we've got 4 of the 6 outcomes that could be A or B. So if you're using the Venn, you would just quite literally say that. So we would now just say 4 out of 6, which is 2/3. This pen is very thick, but anyways. Or you're going to use the probability rule like we did in the last question. What you need to bear in mind now, though, is there is an intersection between A and B. There is one outcome that is common to both of those, the 4, and we need to accommodate for that. So if we use the rule, the probability of A or B, so we're looking all, but we're going to roll with it, is the probability of A, which we already know is 1/3, plus the probability of B, which we know is 1/2, minus the intersection. There was only one outcome, so 1 out of 6. And you type that into your calculator. Please don't do an LCD and all of that nonsense. It's not what we're testing here. Type it into your calculator. And this gives you 2/3. Exactly the same answer. So again, I don't care. You do a Venn, don't do a Venn, whatever. Just back to the question of how many marks is a Venn diagram. You will not get marks for this Venn diagram, because remember I said earlier, I didn't ask you for a Venn. So you won't get marks for it, but it does obviously help you to answer the questions. The only time you get marks for a Venn is if the question specifically say draw a Venn diagram for the situation or whatever the case is. But otherwise you don't just get marks for it. Okay, so the last question says, are events B and C independent? Give a reason for your answer. Okay, so remember event B was the probability of drawing an even number, which had a likelihood or a probability of 1/2. And event C was the likelihood of drawing a 4, which had a probability of 1 out of 6. Now, this is the rule that you have to know. You have no choice in the matter. If events are independent, the probability of A and B must be equal to the product of those two events' probabilities. Okay. When it says give a reason, this is now where we want you to go mathematically prove it. Now, what's important, guys, is you cannot go and work with this as an equation. If you work with this as an equation, you are already assuming that they're independent. We don't know that they are. We need to prove that they're independent. So what we kind of need to do is like a trig identity is prove the left-hand side is equal to the right-hand side. So if we go left-hand side, that's the probability of A and B. Now, we've already worked out in the previous question what the probability of A and B is, because we needed that in our probability rule. So we already know that that is 1 out of 6, or 1/6. The right-hand side is the product of those two probabilities. So the probability of A, I don't know why I'm working with A and B. Okay, so it's B and C, you know, here I am, living my life incorrectly. Apparently erasing everything that I want. Right. Left-hand side. Probability of A, B, and C. Chaos has ensued. Right. A and C, there is no intersection between the two. So the probability of A and C occurring is 0. Guys, why am I working with A and C? Someone needs to come and smack me over the head. B and C. Oh, right. B and C. There is one outcome common between the two of them. Oh, golly. So 1 out of 6. And then I wrote B and B. My brain is working. The rest of me is not with it. It's just a letter and I'm getting stuck. Okay, we got there way too slowly. Anywho, right, then chaos ensued again. The probability of B and C, there's one common outcome, 1 over 6. Right-hand side, I'm not even going to try to be fancy here, we'll just carry on in the same color, is the probability of B times the probability of C, which is a half times a 6. That's it. So a half times a 6 is 1/12. What we can now see is that the probability of B and C is not equal to the product of those two events. And so therefore they are not independent. Now guys, please don't say they're dependent. That's not a thing. They are just not independent. I know it seems really silly, like I'm fully aware of that, but it's the same as like when you do proportion. Just because it's not direct proportion doesn't mean it's inverse proportion. There's other types of proportion that you can work with. So just because it's not independent doesn't mean it's dependent. You just say not independent. Okay, that's it. Sure. Who would have thought writing letters would be so complicated? Not me. But Layla, I felt you there. You can laugh at me. I'm okay with it. I was laughing at myself. All right. So guys, that is pretty much in one relatively long example what probability rule entails. Okay, it's looking at events, determining their probabilities, saying whether or not they're mutually exclusive, independent, all of those things, and working with the information that you have. Right, so let's take a screenshot of that. We do, Leila. That was just, yeah, that was a bad one for me. Yeah, back myself, shouldn't have done so. Okay, so there's the first 4. And E, F, and the dreaded G, that's will now haunt me, but it's okay. I also have 3 Fs here, apparently, so we're doing well with the alphabet today. All right. Okay, so let's have a look at example 2. Now, this is sort of how we phrase questions in exams, where we give you information about certain aspects of your events, and we expect you to answer questions. So it says 2 events, X and Y, are such that the probability of X is 0,4, the probability of Y is 0,3, and the probability of X or Y is 0,6. Determine the probability of X and Y. Now, we haven't told you anything about whether they're mutually exclusive, independent, nothing. So that just means you go back to your good old probability rule and you work from there. Now, remember, this is given to you on your formula sheet. So the probability of X or Y is equal to the probability of X plus the probability of Y minus the probability of X and Y. Okay, again, this is on your formula sheet. You do not need to know this off by heart. But now you just substitute in what you know. So you've been asked to determine the probability of X and Y. So if you look in your formula, that is the very last term in your formula. So we're just substituting in, and essentially it's like solving for X. So we know that the probability of X or Y is 0,6. Let's just write that meter. So 0,6 is equal to the probability of X, 0,4, plus the probability of Y, 0,3, minus that value that we want, probability of X and Y. If you want to shuffle terms around so that you've got probability of x and y by itself, absolutely fine, you do you. It's up to you. But inverse operation says that we should subtract 0, 4 and 0, 3 on the left-hand side. Now 0, 4 and 0, 3 is 0, 7. So we would have 0, 6 minus 0, 7 is equal to minus the probability of x and y. And so when we solve for this, just to get our signs right, probability of x and y is equal to 0, 1. Now, guys, what you need to take away from this is that's algebra. It's an equation. You're solving an equation. Just because there's probability stuff thrown in there does not mean that it needs to be overcomplicated. It is just solving a linear equation. Imagine that probability of x and y as a variable. That's what you're solving for. That's it. Right, something like example 3. I'll come back so you can screenshot in a second. I just want to do example 3. Something like example 3 is now where we're giving you a bit of information about your events. So it says 2 mutually exclusive events. The second you see that, you automatically know that they have no intersection. So the probability of A and B, both of them happening at the same time, is 0. That's what that means. So 2 mutually exclusive events A and B are such that the probability of A is 0, 3, and the probability of not B is 0, 4. Determine the probability of A or B. Cool, right? Now, again, you can go back to a probability rule, which we'll get to in a second. But remember, we've been given the probability of not B. We obviously need the probability of B if we want to go and work with our probability rule. So what that means is we need to go and work out what B is. Now, again, this is where I would just use that little formula. The probability of B is equal to 1 minus the probability of not B. Now, we know the probability of not B is 0, 4, so it's just 1 minus 0, 4, which is 0, 6. Now I can go back to my probability rule. So my probability rule says to me that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. But because they're mutually exclusive, we know that that last term is 0. So all we have to do is actually say the probability of A or B is the sum of the probability of A, which is 0, 3, plus the probability of B, which is 0, 6. So the likelihood of A or B happening is 90% or 0, 9. So when we give you specific information and we tell you these events are mutually exclusive, independent, whatever, then you can go and use that information in your working out. There's nothing wrong with now saying, okay, cool, I know they're mutually exclusive, so my intersection is 0. You can also have here minus 0 because the probability of A and B is 0. You don't have to say minus 0. You can if you want to, but the reason we don't subtract anything is because they are mutually exclusive. Right, so I've just made it a touch smaller for you to screenshot those two. All right. Okay, so guys, that is just your probability rule, using your probability rule. This is grade 11 work, so if you need a bit more revision, go back to your grade 11 notes. But probability, like I said, is a section where you can just bank those marks. And just reading your question carefully, understanding what it's asking you to do, that's half the work done. Once you've got that,